Colin Raffel. I'm currently a senior research scientist at Google Brain, and I'm joining UNC actually as an assistant professor next fall. But for the time being, I'm at Brain.
Very cool. I guess I'd probably get in trouble if I didn't point out that that's my wife's alma mater, so she'll certainly approve.
My wife did her master's there, so...
Well, in good company then.
Yeah.
So I asked you to come on the show to discuss the paper you and your co-authors recently published, Exploring the Limits of Transfer Learning with a Unified Text-to-Text Transformer. So maybe to kick things off, even though the name kind of is self-explanatory, what is a text-to-text transformer?
The distinction that we're making there is that in this paper, we cast every text problem, so every natural language processing problem, as a text-to-text problem. And what I mean by that is that whether you're doing text classification, sentiment analysis, textual entailment, or whether you're doing machine translation, translating from French to English, or if you're doing summarization, whatever, we cast the problem as a text-to-text problem. So, for example, if you want to determine if a sentence is grammatically correct, you'd feed the sentence into the model, and the model would output something like correct or incorrect, like the literal word indicating the correctness of the sentence. If you wanted to translate English to German, you would feed in a string to the model, something like translate English to German, and then the text that you wanted to translate, and the model would output the German translation. And the reason we do this is that it provides this general framework that can be applied to a huge variety of tasks and it allows us to try out a bunch of different ideas that have been proposed in the last couple of years in the NLP space.
I like the framework, and it's sort of intuitively appealing and logical, I think, to most readers. Perhaps, I could sit here and scratch my head and say, is there some way in which it's not robust enough? Like what about a regression task or predict a probability? Can we cast problems like that into a text-to-text transformer in some elegant way?
Yeah, so the funny thing is that we did actually include a regression task in our suite of tasks that we evaluated on. It's called STSB. And the goal of this benchmark is to predict a floating point value between 1 and 5 that indicates how similar two sentences are. What we ended up doing in that case is just quantizing the ground truth floating point values to the nearest 0.2. So for example, 3.35 would become 3.4. And then we convert that floating point value to a string. So literally 3.4. And the model is trained to predict that string. And so what we've done is we've basically taken this regression problem and turned it into a roughly 21 class classification problem. We're training the model to predict these floating point values. It turns out that that range of precision is enough to get state-of-the-art results on this task. You don't have to be so precise. If you think about it, if you and I tried to annotate how similar two sentences are, we probably aren't going to be in agreement within 0.2. So even having this sort of error of upwards of 0.2 from quantization isn't a big deal in that case. While it's a little bit funny that that's how we handle it, just basically converting floats to strings, it does actually turn out to work well and achieve extremely competitive results on that benchmark.
Yeah, I think any criticism there is a fairly weak one. If you asked me to score similarity tasks, I don't know that my personal ratings would be more consistent than that on a day-to-day basis.
Yeah,
so,
exactly.
So early on, and maybe this will expose some of the bias of my interests in theoretical computer science, but when we're talking about machines that output correct and these text-to-text transformers, and especially to see the word limits in the title, I started to wonder if Kurt Gödel and Alan Turing were going to make an appearance. We don't really go in that direction. So what exactly do you mean by limits?
Yeah, so the limits that we're exploring in this paper mostly pertain to the limits of how large we can make these models and how much data we can train them on with the current hardware that's available. So we trained a model that had around 11 billion parameters on about 750 gigabytes of text, or about 1 trillion tokens, bigger and more data than people have considered in the past. And this isn't the only thing we did in the paper, but that's kind of what we mean by the limits. While I think everyone knew that these approaches were pretty scalable, and I think many other people were surprised by how the performance just continued to get better and better. And specifically, there was a benchmark called Superglue. Superglue was proposed about 7 months ago, and it was designed to consist of tasks that were hard for sort of the best text models that we had at the time, namely BERT, but easy for humans. For the most part, by using our text-to-text framework and really not a lot of additional new technology except scale, we were able to go from a huge gap in human performance to basically matching human level accuracy on the Superglue benchmark. The fact that this benchmark that was designed to be difficult for machines could be, loosely speaking, solved by a very similar algorithm that was just made bigger in terms of the number of parameters and the amount of data that it was trained on is still somewhat surprising to me.
So that 11 billion number, for me personally as a reader, I'm starting to kind of lose perspective almost. Like when you talk about the richest people in the world, it's funny money to me after a certain point. Could you frame the jump forward with your project in sort of the context of, was this a 20% gain over what other people were doing, or how extensive of a leap forward in terms of parameters and scale is taking place here?
Yeah, so the common model sizes that people have been using for the past year have been on the order of 100 million parameters. So let's say 100 million or maybe 300 million parameters. It was about a 2 orders of magnitude increase in model size, which loosely speaking represents how big we can make these models and still train them on existing hardware in a reasonable amount of time. Yeah, I guess one thing that I would want to mention is that scaling is not the most satisfying solution to these problems. It's great that we can get good performance by making the model bigger, but currently it's still expensive to run inference on our biggest model.
Can you maybe frame that? I know you may not be in the finance department and know dollars and cents wise, but and of course these costs are usually headed downward all the time, so this will not age well. But perhaps we can frame it in terms of what would buy me a house or a new car or something like that. What sort of price points are the big models really costing?
As you said, it's a little bit hard to estimate. For all of our models except the biggest model, you can fine-tune the model to pretty good performance on a new task in, let's say, a few hours on a single Google Cloud TPU. And Colab gives you the TPU for free. You can also get the TPU from Google Cloud, and I forget the hourly rate. I'm sorry.
But it's free. You can do this with no money.
Yeah, exactly. The problem is that our 11 billion parameter model, you can't actually fit on the single cloud TPU. You need to get a bigger slice of that accelerator that I mentioned earlier. And in order to get the bigger slice, you can't do it on the free Colab TPU. Off the top of my head, I'm not 100% sure how much it would cost to do this fine tuning on our biggest model. But I guess the point is that no one complains when you make models more efficient. And in particular, I can't imagine running inference on one of these models on a mobile phone at this point, for example. Not to mention, the free Colab TPU.
And in terms of architecture, obviously there's a lot of inspiration that leads to something like this, but there's also some novel components to your paper. Can you contrast a little bit about what's new and different from previous approaches to the encoder-decoder architecture?
The funny thing about our paper is that a lot of the success in transfer learning for natural language processing in the past year have been using models that look like BERT, which people have been calling an encoder-only architecture. And what that means is that basically we're feeding text to the model, and the model is doing some processing to that text, and then at the end, it's outputting a single token that indicates the classification that you want to make, for example. This was a change from the original transformer architecture, which was an encoder-decoder architecture. In our paper, because we're casting everything as a text-to-text problem and not as a text classification problem, which is what BERT or XLNet or many of these other models were designed to do, because we're actually doing text-to-text, we use the original encoder-decoder architecture. And in fact, overall, the model architecture is very similar to what was proposed in Attention is All You Need from the original transformer paper. Our goal actually was not really to introduce new model architectures, new pre-training objectives, or anything like that. We instead were trying to take what was available to us in the field, do a big systematic exploration of all of these different ideas and components, figure out what works, and then eventually scale it up. There are some minor differences in our transformer. For example, we use relative position embeddings, which have been introduced subsequent to the Attention is All You Need paper. But otherwise, our model is very similar to just a vanilla transformer.
Thanks to this week's sponsor, GiveWell. GiveWell identifies the charities that save or improve lives the most per dollar. One of the most impactful programs that GiveWell has found is the distribution of long-lasting, insecticide-treated nets for protection against malaria. In Africa, malaria kills about 400,000 people a year and is one of the leading causes of death in children. A meta-analysis on the impact of these nets, highlighted by GiveWell's research, demonstrates the effectiveness of these nets over other treatments. GiveWell then looks for the charities that distribute the nets most effectively. GiveWell combines the findings of the studies, models impact, considers evidence, and studies the rate of malaria in different regions to estimate the impact of a donation. They identified the Against Malaria Foundation to be a particularly high-impact charity, able to distribute the nets for less than $5. And the Against Malaria Foundation has demonstrated the need for more funding. A donation can accomplish amazing things when it's directed to a high-impact charity. And new donors' donations will be matched up to $1,000 when you visit givewell.org/dataskeptic. That's givewell.org/dataskeptic. So we've covered multitask learning on the show in a number of contexts, so I'll take for granted listeners know what it is. And your paper certainly continues a trend we've seen of here's several seemingly different tasks that baselines are being broken on and whatnot. Can you tell us a little bit about the specific data sets? We've touched on it a bit, but the ones that you really highlight in the paper and why you think your approach allowed you to get the gains that you saw over the best in class.
The basic framework that we use in most of the paper is to pre-train the model on a big unlabeled text data set using some unsupervised objective, and then fine-tune the model on a wide variety of what I like to call downstream tasks. So these are supervised learning tasks that you actually care about the performance on. In that setting, the model, it's never really a multitask model because when you're fine-tuning it independently on each task. So for example, at the end of the day, you have one model that can perform translation and then a different set of parameters that can perform sentiment classification or whatever. It's not one model that can perform many tasks at once. We did run some experiments in the paper on multitask learning where basically we do want to have a single model that can perform all of these tasks at once. When you're targeting as many tasks as we are, we're targeting about 24 tasks. It gets hard to set what I would call the mixing rates between the different tasks. So how often do I train on an example from a given task? I have 25 tasks. Maybe I train on one task 100 times more often than the other task. It gets difficult to set those mixing rates, and we ran some experiments to compare that. The other piece that I'll mention that's new in our paper is we introduced a new unlabeled text data set that we're calling C4, which stands for Colossal Clean Crawled Corpus. And what C4 is basically we take the Common Crawl web scrape, which is a publicly available web scrape. It's published every month. We extracted text from the web scrape, duplicated it, cleaned it up, removed any kind of noisy text, anything that didn't look like a sentence or natural text. For 1 month of Common Crawl dump, we were left with about 750 gigabytes of data. The nice thing about this is it lets us train the model for as long as we want on the unlabeled data without really observing any amount of overfitting on the pre-training data. So that piece was a little new, but overall the paradigm of doing unsupervised pre-training and then supervised fine-tuning on the tasks you care about is a pretty standard thing.
Well, I find C4 kind of exciting in that Common Crawl is a mature project and it's kicking out a lot of data automatically. If this pipeline is set up, it seems like we're going to have an easy access to large volumes of generic text data that can be useful for projects like this. Can you talk about how people might, first of all, benefit from it, but maybe also be contributors if there's presumably next steps on it?
Yeah, absolutely. The really nice thing about transfer learning for text, all of the success comes from unsupervised pre-training, and it's very easy to get natural text from the web. And in the past, in BERT, the pre-training data set was Wikipedia and the Toronto Books Corpus, which was a good place to start. But there's really a lot more natural text that's available. And the nice thing about Common Crawl is that they do the scraping for you. The scraping takes a huge amount of engineering to do, but they provide the scraped text, and our pipeline then basically takes all of the very, very noisy, unnatural text on the internet and tries to get as much natural text out of it as possible. We did a pretty good job of getting clean text out of Common Crawl, but there are definitely additional things that could be done to make sure the text is as natural as possible. For example, I think there's a lot of text in this data set that are descriptions of products. And one of the things we found in this paper was that if you pre-train on what I would call in-domain data, so then your downstream performance gets better. So for example, if you're working on the record benchmark, record is a question answering task on news articles. And if you pre-train on news articles, on data from the news, then your performance on record gets better. But when we scrape information from Common Crawl, we don't know whether it's news, we don't know whether it's a product review, a discussion on a message board, a Wikipedia article, etc. And so doing better work to be able to say, my downstream task is in domain X, give me domain X data from C4, I think would result in really substantial gains.
So casually, I've been asking listeners for a while now about their machine learning experience, specifically around hyperparameter tuning and playing with loss functions. And for the most part, I'm finding that although people are aware of the opportunity to use alternative loss functions, very rarely does someone get to put that into practice. Could you talk a little bit about what you guys did in the work and why you got to explore that often unexplored territory?
I'll say two things along those lines. The first is that one of the nice things about the text-to-text framework that we used is that you actually end up using, as far as the nitty-gritty loss function, you use the same loss function for literally everything. For pre-training, for our text classification tasks, for translation, it's always maximum likelihood, which is, your model outputs a probability over the next token, and you train the model to predict the correct next token.
Right. I misspoke. I meant the learning rate. Sorry. But keep going if you wanted. That was an interesting thought too.
The nice thing about that is, as far as hyperparameter tuning and trying to figure out how to make your model work best and all of these different choices, it really removes a lot of the choices. And I'm a big fan of machine learning models and approaches that simplify things. As you and your listeners probably know, the more hyperparameter tweaking you have to do, the more likely it is for you to have trouble training a good model. Because everything uses the same loss function and the same decoding procedure, we can use exactly the same learning rate, exactly the same batch size, all of these factors that people usually tweak. As soon as you get it working on one task, it works for everything. So for every task, every pre-training experiment, we use the same learning rate schedule and everything. And I think that makes a huge difference in practice for practitioners. As far as other design choices and hyperparameters, the bulk of the paper actually is sort of a big systematic empirical study of a lot of the design choices that people make when they're doing transfer learning for NLP. So, for example, we have an experiment that compares different unsupervised objectives. How do you take unlabeled text data and train your model to basically extract information from it? We have another experiment considering a couple of different variants on the model architecture. So we consider a decoder-only language model, our encoder-decoder, etc. For the factors that matter, we've explored them pretty thoroughly. And for most of the other factors, the nice thing about the text-to-text framework is you can kind of just leave them fixed.
I was reading this paper with a couple of colleagues, and for many of us, it was an introduction to the idea of attention masks. Could you talk about how distinctively you're using that in your project?
Yeah, absolutely. So when you have a model that uses attention, one of the pieces that you can manipulate is this what people call the attention mask. And what the attention mask usually does is it either lets the model attend to everything, so the entirety of a sequence, or it only lets the model attend to the future. So for example, if I'm predicting a sequence and I want to predict the next token, but I don't want to allow the model to look at the future tokens, I should modify the attention mask so it only can look at tokens from the past. The reason this is important in our paper is a language model, which is just trained for next step prediction, uses this causal attention mask where you don't allow the model to attend to the future. But you can tweak that architecture a bit and basically allow the model to attend fully without any masked out sequence entries for the first part of the sequence, and then ask it to attend causally for the rest of the sequence. And we want to do that in our case because, again, we're using a text-to-text framework. So when we use a language model, we concatenate the input text with the output text when we're training the model. And we want to give the model full context for the input and then force it to generate text with a causal attention mask for the output.
So as you were mentioning, the paper is a nice exploration of a lot of those different sort of, they're almost hyperparameter tuning things, right? Like the decision choices about network style and whatnot. Were there any that stood out to you that you thought were especially insightful and useful for NLP tasks?
I think one thing that this paper does as far as architecture, since we were just talking about architectures a little bit, is we try to be a little more rigorous when we're comparing decoder-only language models to an encoder-decoder model. We try to compare them not only in terms of the number of parameters, but also the number of flops that it takes to process a sequence. And a lot of times, especially in the NLP community, people, they kind of are more interested in the number of parameters, but we argue in this paper that the number of flops required to process a sequence is also quite important. And one of the interesting findings from exploring this parameter flop trade-off was that if you actually share the parameters in the encoder and the decoder, the performance doesn't drop very much. So that's just one interesting tidbit. Another takeaway that was a little surprising to me was that across many different unsupervised objectives, we didn't find a huge difference in performance as long as you were doing some form of denoising. And when I say denoising, I mean that you're taking the unlabeled input text, you're corrupting it in some way, for example, by removing tokens, by replacing them with random tokens, whatever, and then you're training the model to predict the corrupted tokens. So as long as you're doing that, we found that the model could obtain pretty good performance, and different ways of corrupting it or changing the amount of corruption didn't have a huge impact. The last little takeaway that I'll just mention is, we spent a good amount of time doing a bunch of cleaning to Common Crawl to get C4. As you might expect, if you don't do the cleaning, you get a lot more data. So you get about 10 times more data, but the performance on all of your downstream tasks gets worse because your model is learning to model noisy, bad text. We can be reasonably confident that the cleaning that we do in C4 is useful.
So thinking about how different practitioners will take these to market, so to speak, whether that's, they take advantage of language systems to produce some product like a machine translation system, or, a researcher is going to use this for their thesis or what have you. There's a lot of directions they can go in terms of scale. Do you think people like that are going to benefit from longer training time or, getting better pre-training models from other people? How does a smaller individual who's not backed by a large team and a large bank account get involved in NLP and take advantage of some of the transfer learning techniques that are out there?
One of the things we tried to do in this paper is to make these results as useful as possible for any practitioner out there. And so one thing we did is we released all of our pre-trained models. And that really, I think, is one of the reasons that transfer learning has been as successful and impactful as it has. If you're a practitioner and you want to train a model that, in our case, does really any text task, so a text classification task, a summarization, whatever, you can take one of our pre-trained models and with relatively little fine-tuning, with relatively little supervised training on the task that you care about, you can get pretty good performance. Because the model has been pre-trained for so long, it doesn't take that many update steps to get good performance. So even for these bigger models, it's not terribly expensive. The expensive part is kind of paid ahead of time when you do the pre-training, because it does require, like I said, we're training an 11 billion parameter model on about 1 trillion tokens of text. That takes a ton of computation. But once you've already done that, you've sort of amortized the cost, and it makes it much cheaper for a practitioner to use the results. The difficult thing is that if someone wants to come along and develop new unsupervised objectives or model architectures, and they do have to pre-train the model, that piece can be definitely expensive.
Yeah, I think that's true, but probably rarer and rarer given the robustness of a lot of the pre-trained offerings that people like yourself are sharing. What's the lowest hanging fruit for someone to go out there and get their hands dirty and explore or perhaps even apply the power of some of these pre-trained models to their unique NLP task?
Yeah, so we actually very recently put out a Colab notebook, which is kind of like a Jupyter notebook, that allows people to fine-tune our model T5 in their browser on a free Google Cloud TPU. And so if you just have some text task, and again, hopefully it should work well, whether it's text classification or a sequence-to-sequence task like translation or summarization, you can basically show the model where to grab your data. It could just be in a tab-separated value, a TSV file. The model will fine-tune in your browser, hopefully on the order of a couple of hours, and you can sample from the model and evaluate it to see how well it's doing. That provides a very straightforward way to try out these models. We also, as I said, we released all of our code. So if you want to dig a little deeper, you can grab our code base, and we have a pretty nice API for adding new tasks, fine-tuning the model, evaluating it, etc. And there's a link to that code in our paper right on the first page. So you can kind of engage at any level you want. If you want to pre-train the model again and reproduce our experiments, that's doable. If you want to go a little less in depth and just fine tune it, you can use the Colab or use our code base on GitHub.
Sounds good. I'll have links to all that in the show notes so people can follow up there as well. After completing the paper, I noticed the title is Exploring the Limits. So there was no promise of telling me the exact limits. But I'm curious if you have any thoughts on sort of the asymptotic design here. Can we just keep putting in larger and larger data sets and seeing better and better performance?
Well, the funny thing is, and I really didn't expect this outcome, but for most of the tasks that we include in this paper, in my opinion, we have basically saturated them. So for example, on Glue, which is a collection of benchmarks, we're now above human performance on most of them. For Squad, we've been well above human performance for a long time. As I mentioned, for Superglue, we're roughly at human performance. CNN Daily Mail, we're above human performance. And the translation tasks, we have also basically reached human performance. While we definitely did see gains from making the model bigger, it's not clear how meaningful additional gains would be on these tasks. So there's actually a lot of really excellent work in the NLP community right now trying to design harder and harder tasks that are difficult for models like this to solve, which is, as I mentioned, how Superglue was designed. So it's kind of a continual process. We develop new ideas, new approaches, scale up existing approaches to attack problems. We might be able to get good performance on those problems, and the community comes back and gives us harder problems to work on. One paper that I'll point out specifically that tries to make this cycle a little more explicit is called the Adversarial Natural Language Inference Benchmark. And in that benchmark, they actually put a human in the loop who queries the model and figures out how to fool it. And then the model takes the examples that it got wrong, retrains itself, and then the human tries to fool the retrained model, and they continue this process explicitly. So I think approaches like that will help us sort of figure out where the gaps are in the abilities of these models.
To wrap up, Colin, where can people follow you online?
Yeah, so I'm on Twitter, of course, twitter.com/Colin Raffel, and also website colinraffel.com. You can find me on GitHub. So we posted this paper on Archive. We're hoping to submit it somewhere later on, but we haven't had any sort of explicit peer review process for this paper. And we really want feedback. So if you have any criticisms, questions, or concerns about the paper, reach out to me because I'm always interested to hear what people think.
Well, you may have just started a new trend in the peer review process. I hope you get some emails.
Yeah.
Awesome, Colin. Thanks again for taking the time to come on the show and share your experiences.
Thanks for having me.